So, very good afternoon to everyone, all the participants here, speaker, and other people present. We are in the third day of the program, and we are going to have probably the sixth lecture. And I hope you are just Sachin is incredible. His one lecture has gone, and this is a very interesting topic. So I hope everybody will enjoy. I request Sachin to please start.
Okay. Thank you so much, Atri. Good afternoon, everyone. Today, I'd like to tell you a little bit about non-abelian gauge theories. Now, you might have heard about something like this, and at the outset, it might seem intimidating and strange. So, I'd like to argue today that there is a very nice intuitive way, at least to have a working understanding of what a non-abelian symmetry, what a non-abelian gauge theory means. So that's why my talk is titled Group Theory, Robotics, and Low Energy QCD. So when I say low energy QCD, I'm going to, this is the part that is going to connect, that is about non-abelian gauge theories. The robotics part, which might come as a bit of a surprise to you, is about the emergence of gauge symmetry. And the group theory, of course, this is a conference, this is a workshop on group theory. So we should really talk about group theory, isn't it? Okay. So I'm going to start off by reminding you a little bit about the motion of reticulated or extended bodies, which goes nowadays by the name of robotics. And the way that we, or mechanical engineers, understand robotics and robot dynamics is by studying the configuration space of these extended or reticulated objects. These are called, this is called the shape space. And as I will argue, gauge fields emerge very naturally from the space of shapes. Now, if you were to quantize such a system, then you get quantum robotics. And from there, it is a very short step, if you like, at least intuitively, at least conceptually, to look at non-abelian gauge theories, because as I will argue, this is nothing but quantized dynamics in shape spaces of a particular kind. What is remarkable is that these shape spaces, the ones that I will talk towards in the second half of my talk, appear very naturally in particle physics, and in particular in this theory called quantum chromodynamics. So I'll tell you a little bit about that, and that's where we will end. Okay. Now, robotics, of course, has a long history, and the reason why human beings have looked for towards robots or robotics is a hope that any repetitive or dangerous activity may be automated, and this desire to take the human being out of the repetitive or dangerous activity is quite ancient. There have been early attempts. A clock is an example, if you like. It's a mechanical device that keeps time. You don't have to have a human being who has to count from 1 to 100 again and again and again and again. There are examples of artificial birds and animals, and even warriors. And here is a picture that is an example of a robotic warrior that was designed by Leonardo da Vinci. And there's, of course, a picture of him, of this robotic warrior, one with his armor, and another with the insides of how the robot's arms and head, for instance, is supposed to move. So this mechanical knight, as Da Vinci called it, is capable, provided you have the engineering to construct all the parts. It's capable of sitting or standing, waving arms, moving its head, and so on. So, as I said, human beings are interested in having mechanical objects or mechanical beasts which will help us get rid of, take human beings out of the equation when their activity is repetitive or dangerous. Okay. Well, of course, I want to start off with a very simple example. And the simplest example of such a machine that has internal paths which moves with respect to each other. And if you like, this is almost trivial. A hinge, I have two rods, and the rods are joined in the middle by a hinge. This, if you like, is the simplest example of such a machine. You can string together more rods and make a snake out of it. For example, here in the picture that I have, in the second picture that I have strung together 1, 2, 3, 4 rods, and there are 1, 2, 3 hinges that connect them. Okay. The point is, as a scientist or an engineer, what we would like to understand is how do we study the motion of such objects. And the reason we want to study their motion is in order that we are able to control the motion. Well, first thing we can do is to separate out overall rotations and translations from internal motions. And this has an obvious advantage, because if you separate out these overall rotations and overall translations, then we have fewer coordinates to worry about. And fewer coordinates is always better. Once you have separated out these internal, these overall rotations and translations, then we can start to assign internal coordinates. For example, we decide that the relative angle between the arms is one of our dynamical variable. And this, as the relative angle changes, the shape of the hinge changes, and the dynamics that leads to this change is therefore the dynamics of this hinge. One thing you notice is that because we are looking at a system in a plane with no other forces or external torques, the orientation of this hinge with respect to a fixed coordinate system is not so important. And this is again related to the fact that we have separated out overall rotations from internal rotations or internal motions. But this separation is going to have dramatic consequences, and I'm going to give the game away right now by showing that this leads to this amazing emergence of gauge fields. Okay, so let's see how that goes. So let's start off with the first example, which is nothing but the hinge in a plane. Okay? There are no external torques acting on the body, and because there are no external torques, the angular momentum is conserved. So in particular, we can start off with a situation where the total angular momentum of the system is 0. Okay. So let's start off by arranging the hinge so that both rods are on top of each other. Of course, I didn't want to draw it like that, because if I drew it right on top of each other, then you would just see one rod, and it might be a little bit confusing. So I have drawn it in which the two arms are slightly separated, but this is really what we have in mind. So the starting configuration is what I call the configuration A, when the hinge opening angle alpha is 0. Now, what do I do? Imagine that we have tiny motors, a tiny motor that sits on top of the hinge and spreads one arm away from the other arm, like in picture B. Okay. Of course, if you were to push one arm away from the other arm, because the total angular momentum is 0, the second arm has to move in the opposite direction, right? If I move the first arm in the clockwise direction, because the total angular momentum is 0, the second arm has to move away in the anti-clockwise direction. So let's keep doing that. Let's keep pushing and pushing till we arrive at the picture C, when the hinge opening angle is 270 degrees. And finally, when we push it all the way around, the hinge appears to be fully open, if you like, or equally valid way of saying that would be fully closed, because now the opening angle is 360 degrees as shown in figure D. So we have changed the internal angle, internal dynamical variable A, which is the opening angle, all the way from 0 to 360 degrees. This is what we have done as we have gone through the sequence A through B through C through to D. Okay. But now let's look at the picture. Let us look at the configuration A and the configuration D. Notice that they are almost exactly the same, except that the body, this machine or this hinge as a whole has rotated by 180 degrees. This is like saying that if you took the configuration A and then rotated it by some external, rotated it as a rigid body by 180 degrees, you arrive at the configuration D. But that's not what we did. We performed only internal motions. And what we see here is that internal motion can lead to an overall rotation. So here, an internal motion where the opening angle changes by 360 degrees led to an overall rotation of the hinge by 180 degrees. Now, of course, if you think a little bit about this, you might think, oh, but what's the big deal? I mean, this is, I mean, maybe we are just playing with words when we say that, oh, we are just playing word games here. Well, let me give you another example, which is a little bit more complicated. And this is an example of 3 rods that are connected by 2 hinges. Okay, so I have 3 rods. I have labeled them as the rod 1 is a rod that goes from 1 to 0. The rod 2 is from 0 to 2. And the rod 3 is from 2 to 3. These are 3 rods, and there are 2 hinges, one at 0 and the other at 2. Okay. So what are we going to do? I'm going to show you a series of motions, and at the end, we will start from some particular configuration and we will end at the same configuration, but the system again would have rotated as a whole. So let's start. So I'm going to go through these diagrams A, B, C, D, and end at E. Okay. So let's start. My starting configuration is A, in which 0, 1, the rod 0, 1 is aligned with 0, 2, which is itself aligned, which is in the same line, collinear to 0, 3. And again, strictly speaking, this 0, 1, the rod 0, 1 should be sitting right on top of the rod 0, 2, but then you wouldn't be able to see that there are 2 rods. So I've drawn them slightly separated. So there's a vanishingly small opening angle between the 2 rods 0, 2 and 0, 1. Okay. Now let's do the following. We are going to unfold the rod 0, 1 till the angle between 0, 1 and 0, 2, 3 is 90 degrees. Again, there's no external torque. Okay. So if I want to unfold the rod 0, 1, then I have to push against this rod 0, 2 and 2, 3, right? So as the rod 0, 1 unfolds, as it rotates counterclockwise direction, the rest of the composite rod 0, 2, 3 moves in the opposite direction. So what we're going to do is we're going to do that until this opening angle is 90 degrees. So that is what the picture B looks like. Fine. Now what we're going to do is we're going to take the rod 2, 3 and fold it. The rod 2, 3. So right in position B, we have rods 0, 2 and 2, 3 collinear. So now I'm going to take the rod 2, 3 and fold it along the hinge 2. So till this angle 0, 2, 2, 3 is 90 degrees. So again, as I fold this, the other part also rotates because the total angular momentum is 0. So if I fold one part, then the other part has to rotate to compensate for the change, apparent change in the angular momentum in one part of the system. Fine. So now the system looks like in picture C. And now what we're going to do is fold the part 0, 1 back so that it aligns with 0, 2. So this is what I do. I fold this part back, and finally I unfold the part 2, 3 till it looks like a straight line. Again, 0, 2, 3 is a straight line. But what is amazing is that if you sit down and do this calculation carefully, following all the angles and the changes in angles, you find that although the picture E and the picture A are the same, the picture E, in the picture E, this mechanical object has rotated compared to the picture A, and you can compute this. In fact, we will do it. I will show it to you in the next slide how to do it. It has rotated by a relative angle of minus 7.5 degrees. So there's a relative angle between picture A and picture E, and the relative angle is non-zero. So again, by performing purely internal motions, we have managed to change the overall orientation of this body. I'd like to pause here and ask you pause for questions and take them if there are any. Would anyone like to ask any questions about what I just showed you?
Sir,
Okay.
why in the
So let's go on then.
B?
Yeah.
Why in the figure B?
Sorry, which figure?
Figure B. Why
In figure B, okay.
0 to 3 section is rotated from horizontal to a bit.
So imagine that you are starting off from the picture A.
Yeah.
Okay, and again you have a tiny motor on the point 0, which is performing this rotation, this opening of the angle for you. Okay.
Okay.
Now, because the total external torque is 0, the only way you can change this angle is by pushing against the rod 0, pushing against the rod 0, 2, right?
Yeah.
So as you push against the rod 0, 2, the rod 0, 1 will of course will rotate counterclockwise to the position that I have shown, right?
Yes.
But similarly, because you have pushed against the rod 0, 2, that will also rotate a bit.
Okay.
Right?
Yeah.
Okay. And similarly for the other pictures as well.
Okay.
Okay. Okay. Is there any other question? There is a question from Neeraj Kumar, and he asked, is the center of mass allowed to change? So again, in the system that we are considering, there are no net external forces. So no net external torque and no net external forces. So if you want to change the center of mass, when there is no net external force, then you realize that you have to supply net momentum to the center of mass, right? But that would imply that that you are applying an external force, which there is none here. So again, the center of mass doesn't change. I haven't plotted the center of mass here, but it's a small exercise for you, either on the computer or actually even on a graph paper, to go through this sequence A, B, C, D, E, and keep track of the center of mass. And you can see how you can see that the center of mass actually doesn't move at all. So, is there any other question? Okay, so let's see how to make this
Sir,
calculation.
sorry to interrupt.
Yeah, okay, go on.
Here, when we are going from figure A to B, why is the compound rod between 0, 2 and 2, 3, why is it constrained to move together?
Oh, that's that is the particular sequence of moves that I am making. Okay, so when I go from A to B, so if you like, I have a tiny motors which can change the opening angles. I have a tiny motor at 0 and a tiny motor at 2. In order to go from A to B, I turn on the motor at 0, but do not allow but do not allow the angle between 0, 2 and 2, 3 to change. This I can do without applying any external forces. I just have to make sure that I can do this purely by applying internal forces, right? So
Yes, sir.
that's how
we are specifying that is.
The only rule in this game is I cannot apply a net external force and I cannot apply net external torque. These are the only two rules. Other than that, I can do anything else. Well, of course, I'm not supposed to break the rods and the hinges, but yes, other than but yes, that's about it. Other than that, I can do anything. So, I mean, if you want, you can look at other motions in which at the same time you change the angle between 0, 2 and 2, 3. Okay, you can study those motions too. But the point about this exercise is for me to demonstrate that although A and E, the shape of the rigid body is the same, when you go from A to E, the relative orientation of our rigid body or pseudo-rigid body, if that's a more accurate word, the relative orientation of the pseudo-rigid body has changed, although the shape of the pseudo-rigid body is the same in A and E. And I want you to think a little bit about this because there is no net external torque. Nevertheless, we have succeeded in rotating the body from configuration A to configuration E. And this, you must recognize, is quite remarkable given that there is no external torque. Normally, when you have to rotate something, when you have to rotate a body from one configuration to another configuration in a rigid manner, you have to apply an external torque, right? Not here. Here, purely by doing internal motions, we have rotated the body. Just as in the more simple example of the case of two rods, by purely doing internal motions, we managed to rotate the hinge by 180 degrees. I think there was one more question. Okay, so let me continue. So let's see how. Sorry?
Sir, I had a question. Can I tell it now or should I wait?
Yes, yeah, please. Because after this, there is a short calculation and then I would like to go through that calculation in one shot. So please ask your question. Yes.
So my question is the change in relative angle that you have shown is 7.5 degree. This angle is measured in which plane?
So this angle is measured with respect to the fixed coordinate axis. So if you like, let us make a coordinate axis in figure A where let's make a fixed coordinate axis in figure A where the horizontal line is like the x-axis and a vertical line is the y-axis. I have not drawn them here. So that is my fixed external coordinate axis. And with respect to that coordinate axis, there is a relative angle between configuration A and configuration E of minus 7.5 degrees. So the rotation, the overall rotation is with respect to this fixed axis, fixed external axis. There is one question in the chat box from Prasad Basu, and he asks, do gymnasts also use the same technique? Absolutely, absolutely. In gymnastics, you use the same technique as well, and gymnasts use it. Falling cats. You may have
falling cats.
heard.
Yes, falling cats.
You may have heard about this folklore. In fact, I think it is. I wouldn't. None of us should do this experiment on purpose because it would be borderline cruelty to animals. But if by chance you see a cat lose its balance and fall off, you will see that it'll always land on its feet, even though when it started, when its motion started, it was in some awkward position and in an awkward shape, with all its legs flailing and tail waving about wildly. By the time it comes to the ground, it has done internal motions, purely internal motions, so that all four of its feet are pointing towards the ground. So this is another example of purely internal motions of a body which has internal moving parts, and this body has managed to make an overall rotation. So that is another example. So yeah. So gymnasts use these techniques, cats use this technique as well. So this, if you like, is a very, very crude version of a very simple 3-hinged cat. Okay, so do you have any other questions?
Yeah, I do have one question, sir. Regarding the drawing of the picture, have you used a particular software, or how do you measure actually the 7.5 degree? I mean, is there a calculation behind this, or it is just?
Yeah. So in my next slide, I will be showing you how to do this computation of minus 7.5 degrees, and because I can do the calculation, actually do the calculation. When I drew the picture, I must confess that I drew it by freehand. So
okay, sir.
Okay. So shall we look at the calculation? All right.
Yes, sir.
Yeah. So I'm sure that all of you are now very curious of how one calculates this minus 7.5. Okay. So in order to do that, we have to do a little bit of work. So let's put a coordinate system. So what I've done is that I have arranged my 3 rods with 2 hinges, like what I've shown. I've defined for you angles theta, alpha, and beta. Okay. So theta is the angle between the first rod and the x-axis. Then theta plus alpha, if you like. And alpha sort of measures the theta plus alpha gives you the location of the second hinge, and theta plus alpha plus beta, if you like, gives you the location of the third hinge, of the tip of the third rod. Okay. So because of the picture, I hope the meanings of the coordinates are quite clear. Okay. Now you can of course do the actual computation. It's a simple exercise. But what I want to do is I want us to think about this problem a little bit differently, because if you really want to do this computation, it doesn't require anything more than 12th standard or maybe first year BSc knowledge. But let's change our game a little bit and think about this problem a little bit differently. So let's go back to the most important condition, the condition that we impose, that there are no net external torques, and at the start of the game, this mechanical object here that we have here is not moving. So no net external torques, and this initial condition means that the total angular momentum of the system at the start is 0. And because there are no net external torques, the angular momentum will continue to be 0, whatever we do internal to the body, right? Okay. Now, if you remember your classical mechanics, you realize that this condition L equal to 0 is an example of a non-holonomic constraint. So maybe you do remember what holonomic and non-holonomic constraints are, but in case you don't remember, they are, if you roughly speaking, holonomic constraints are the constraints that can be written purely in terms of the coordinates. A more general constraint is a constraint that involves the coordinates and the velocities. Now, of course, constraints that involve positions and velocities sometimes can be integrated to write the constraint in an equivalent form that depends only on the coordinates. The non-holonomic constraints are typically those, non-holonomic constraints are those where you cannot integrate this constraint to write the original constraint as a function of just coordinates only. So the condition L equal to 0 is an example of a non-holonomic constraint. And if you sit down and apply this condition L equal to 0 to these angles, so you write down the velocities, angular velocities. Various angular velocities are theta dot, alpha dot, beta dot, and so on. Then find out the total angular momentum and demand that it's 0. You get an equation like this: 4 plus 2 cos beta times d theta plus 3 plus 2 cos beta times d alpha plus 1 plus cos beta times d beta is equal to 0. Okay. So what we can now remember here that theta is the angle between the first rod and the fixed and our fixed x-axis. So it is like our external angle. So what we would like is to work only in terms of internal coordinates. So roughly speaking, we would like to have everything as functions of just alpha and beta. So I can write this equation. I can massage this equation to write out an equation for d theta in terms of d alpha and d beta, where I have called the coefficients a alpha and a beta as the coefficients of d alpha and d beta respectively. And it's very easy to see what this function a alpha is and what the function a beta is. It's what I have written down. You know, it's these ratios: 3 plus 2 cos beta divided by 4 plus 2 cos beta for a alpha, and a similar function for a beta. Okay. Now let's go back and try to understand what's happening here. And because theta is measuring the orientation with respect to the external axis, the internal motion is therefore described only by the angles alpha and beta, right? We are not going to worry so much about theta, except possibly when we want to measure overall orientations when we go through the sequence of motions A through E, as we had done a couple of slides ago. Okay. What I'm going to now do is call this pair A alpha, A beta as a vector A. When I call it a vector, I'm calling it a vector by a slight abuse of notation. Strictly speaking, its mathematical status is that of a covector, but we won't have time to go into that. But I'm going to call it the gauge potential, and this is a covector or a vector that is induced by the condition L equal to 0, right? That's how we got this, right? This equation, first equation, L equal to 0, gave us the formulas for A alpha and A beta. Okay. Now let's perform a sequence of operations and follow them in the alpha beta space. Now this alpha, which is the opening angle, which is one of the opening angles, goes between 0 and 2 pi, and similarly beta, which is another of the opening angles, goes between 0 and 2 pi. So that's why I have marked the points 2 pi, both on the x-axis, on the alpha axis and the beta axis. And then I've drawn for you a curve. The curve is in black. That's an example of a closed loop. So if I follow this loop, if I make a sequence of motions following this loop, then when I when I end up, I will end up, by the time I end the motion, I would have arrived at the same value of alpha and beta that I started off with. Okay. Okay. Now let's sit down and follow through the motion that we did. So if you remember, the first motion that we did was change alpha by 90 degrees, right? So there you go. The first motion that we do is to go from 0 to pi by 2. That is the, I don't know if you can see my pointer, but that is the first of my red arrow. It sits on the alpha axis, starts from 0 and goes till pi by 2. The next motion is to rotate, is to change beta again by pi by 2. The third motion is to change alpha by minus pi by 2. And the fourth one is to change beta by minus pi by 2. So in the alpha beta space, I have executed a closed loop, which is marked here by my small red square. Okay. Okay. Now, what we can do though is we can compute what is the change in theta, because we know theta as a function of alpha and beta. Here you go. We know d theta as a function of d alpha and d beta. So we can calculate the change in theta by computing this line integral, closed line integral. Is integral a alpha d alpha, a beta d beta for this loop, for 0 0 going to pi by 2 0, going to pi by 2 pi by 2, going to 0 pi by 2 and back to 0 0. And I'll let you figure out why there is an overall minus sign. It has to do simply with the orientation that we chose to follow. Okay. Now this line integral, now you know that from Green's theorem, that line integral can be converted into an area integral, right? So I can write down the line integral, this formula for delta theta. I can write it as integral over the area d alpha d beta, which is the area enclosed by my by my square here, which has red edges. And the function that I'm integrating, I'm going to call it b. Of course, Green's theorem tells you what is the formula for b. It is dA beta d alpha minus dA alpha d beta. Okay. Okay. So we're almost done. You can sit down and do this computation. And I'm not going to do this computation. You know the explicit formula for A alpha and A beta. If you plug that in and compute b and compute this area integral, you will find that delta theta is minus 7.5 degrees, or whatever that works out to be in radians, maybe 7.5, 15, 30, pi by 6, maybe pi by 12 or pi by 24. I don't remember now. So that's what you will get. Okay. So before I go into generalities, again, I would like to pause and see if there are any questions.
Yeah, I do have two questions, sir. So can you please go to slide number 8, sir?
8, okay.
The previous slide.
Yeah.
Now, when you are saying that it is a co-vector, it is clearly seeing that you have written the coefficients of the covector A alpha or A beta as a subscript. Is that the reason, or you have a much stronger reason why?
Yeah. No. The way I have written the subscripts takes into account that it is a covector, but I haven't. But unless I tell you that it is unless I convince you that it is a covector, my choice of notation doesn't mean anything.
So because for me, if I see it is eating a vector and spits out a number, then I will satisfy that okay, it's actually sitting in the dual space. So there is a certain reason I feel, isn't it?
Yeah. I mean, I would say that that we would have to have a sort of a side discussion to understand why this is a co-vector, and in fact, it would take away from the if you like from the magic of this computation, that you use this a little formula that I gave you to actually compute the change in the angle. But
Yeah. No problem, sir. We can do the discussion later, which we should not interfere the, flow of the lecture. And the second
Okay.
question is that, can you please go to the slide number 9?
Yeah.
Now, the way you have drawn the vectors, it is a hunch. I do not know whether it is true or not. Is there some sort of analogy with the parallel transport?
So here you're talking about these little red arrows.
Yes, sir.
Yeah. So the little red arrows correspond to the motions that I did here, right? So here first I did alpha by 90 degrees, then beta by 90 degrees, then again alpha by minus 90 degrees, and beta by minus 90 degrees. So, and these are all straightforward motions. So that is why I drew that is why the sequence of motions is this small square. Okay. But on the other hand, your guess is right, is that when I perform the sequence of motions corresponding to this red square, the function theta is changed by an amount minus 7.5 degrees. So it is really related to it is very closely related to parallel transport, as you suspected.
Yes, sir. Thanks a lot. Because my hunch was, if in the shape space, if you are thinking it as a parallel transport, then I can bring the notion of the curvature and something else. So it is just a hunch.
Yes.
I do not know. You must tell it better, sir.
Yeah. So it is not quite curvature. In the shape space, the A is corresponds to a gauge potential, and this gauge potential is non-trivial, and that is so the since you brought up the question of curvature, when you do parallel transport, if the curvature in that part of the space that you're looking at, if the curvature is 0, then the original vector and the and the parallel transported vector continue to remain parallel to each other, right?
Correct, sir. Correct.
On the other hand, if there is curvature in that part of space, then the original vector and the parallel transported vector now have a relative angle.
Yes.
Right?
Yes.
Here, in this example, the underlying mathematics is such that if the B that you compute out of the A is non-zero, then you will always get a non-trivial delta theta.
Yes.
So the B that I have written here is the analog of curvature, and if there were a sequence of motion, or if there was another system, if there is another system where this corresponding B is 0, then you would find that delta theta. Then you would find that there is no net rotation of the body. So B is like the curvature, and A's are like very, very, very intuitively speaking, A's are like the Christoffel symbols. If you have come across them, then it might make sense to you. But if you don't know what Christoffel symbols are, then don't worry about it. Don't worry about my remark.
So, I thought that A is a vector potential, one form, and the F is the Faraday form, so it is a 2 form. So F is equal to dA. In that sort, I was thinking. So B
you are
is
absolutely right. You are absolutely right to think of what you have said is absolutely right. But because I am not sure about the preparation of the audience, I did not want to introduce more complicated things than necessary. But
it is absolutely fine, sir, from your side. Absolutely fine. Thanks a lot.
What you have said is absolutely correct. I see that there is another question from Harkishan Dua. He asks, suppose I have a periodic system like a graphene or graphene, or 2D systems with buckling line pentagraphene. Okay, and I'm not sure that this. I'm not sure this question is for me. And I know the point group symmetry. How can we identify and deduce the IR and Raman modes? I don't think it has anything to do with what we are discussing just now. Harkishan, if you want to speak, or if you want to, in the chat box, you want to clarify your question, please do so. Otherwise, I will move on to the next question. And if there are no questions, I will go on to the next part.
Hello, am I audible?
Yeah.
Hello.
Who is this?
This is Harkishan, sir.
Yeah, okay. Yeah, please go on, Harkishan.
Actually, I wanted to know, actually, I'm from this molecular physics background.
Okay.
And and in your this, here it is written, you will be discussing about molecular physics, how to understand the spectra. So I just wanted to ask if we could use this knowledge about the point group symmetry of a particular system and use it to deduce the IR or Raman spectra modes, Raman modes or IR. Can we do that?
Okay. Okay. But this question doesn't really have to do with what we are talking about just now, right? It's a more general question, is it?
Yes, sir.
Or do you? Okay. So the short answer to your question is yes, we can use the point group symmetry to identify and deduce both the infrared as well as the Raman modes. But because I have to finish in a finite amount of time, you will forgive me if I take questions only related to this talk. Okay?
So if you could give me your any credentials or email ID, I could discuss with you after this thing also.
We can talk. We can definitely talk after that. And if you have questions about what we are discussing just now, then that is, I think, a better way to use this 1.5 hours, right? We can always discuss other things outside this seminar.
Okay.
Okay. Are there any other questions? Okay. So let's go on, and let me go back to the full screen. Okay. So we figured out how to calculate the change in the angle, and I certainly hope that you go home and do this calculation. Okay. So this leads us to this idea of gauge symmetry. Okay, what is gauge symmetry? Roughly speaking, it's the freedom that we have in choosing the body fixed frame with respect to the space fixed frame. So in all these examples that we were looking at, we could have chosen a frame or an axis which was fixed to the rigid body, and we could have chosen, and there is of course a space fixed axis, and you can choose a body fixed axis in any manner, in any orientation with respect to the space fixed frame. Okay. And what happens is that when you are looking at dynamics of bodies which have internal moving parts, the motion is often constrained. For example, we are interested in motion like net angular momentum equal to 0, or net external momentum is 0. And these constraints are not as arbitrary as we saw. No, if we have a system where there are no net external torques or no external forces, then essentially we have a situation where the total momentum or the total angular momentum is conserved. And if at the start of the game, if these quantities are 0, then they continue to remain 0 throughout the rest of the evolution of the system. Now, these are non-holonomic constraints, and generically, these constraints are not integrable. And when they are not integrable, they lead to emergent gauge fields. In classical systems, if you like, these gauge fields give rise to Coriolis-like forces. So again, if you remember from your 12th standard, when you first or earlier, when you first came across the Coriolis force, it arises in a when you're comparing the motion, of an accelerating body in two frames, a fixed frame and another frame which is relative to the body, and this body is again the motion of this body is, roughly speaking, it's a body with internal parts, and it gives rise to this Coriolis force. And it turns out that if you want to, the best way or the most appropriate way for studying such dynamics is the mathematical theory of fiber bundles, which we will not go into today, but this is really the framework in which one should be studying the dynamics of such systems that have moving internal parts. Okay. Remember that for our first example, we looked at two rods that were hinged together. And naively, this dynamics required 2 degrees of freedom, one angular variable for each rod. But when we impose the constraint L equal to 0, what that meant is that the angular displacement of the second is not independent of the first. In fact, if the rods are of equal weight or of equal moment of inertia, then the angular displacement of the first is equal and opposite to the angular displacement of the second. So because of this constraint, we actually need only one angular variable. The other one is redundant. And what it means is that formally, a way to formalize the statement is that instead of having two angular variables, which I have denoted by S1 cross S1, what you have is a quotienting of S1 cross S1 by the group of overall rotations, SO2, because these are rotations in a plane, that's why SO2. So the shape space of the rods, of two rods with one hinge, is this space S1 cross S1 quotiented by SO2. And don't worry if this doesn't make too much. If you know what this means, it's fine. But if it doesn't make too much sense, all it means is that if you use two angular variables, then that's too much. You have to get rid of one angular variable by taking into account the fact that the total angular momentum is 0. That's what this statement means. Okay. In our second example, we had 3 rods, right? Again, naively, the configuration space would appear to be 3 angles, one for each rod, right? Because each rod can rotate about its hinge by 2 pi radians. So you would think that you need 3 independent angles, each angle going from 0 to 2 pi. But because the total angular momentum is 0, again, we know this is a redundant description. So the true configuration space is 3 angles, but not all of them are independent. So the lack of independence is denoted by this quotient. You have to quotient by the overall set of rotations, which is SO2. And mathematically, this structure is S1 cross S1 by SO2, which was in the previous slide, or S1 cross S1 cross S1 quotiented by SO2. This structure is called a fiber bundle. And it looks like it looks like a space because it has coordinates on it. But what is interesting about this is that very often these spaces can have very interesting geometry and very interesting topology. And this non-trivial geometry and topology is something that can impact the system dynamics and decide the dynamics of many jointed bodies, therefore has a very natural setting in fiber bundle theory. Okay, I'd like to discuss one more example, which is again quite interesting and maybe of interest to people who are interested in things in molecular physics, for example. And the reason why I want to discuss this example is that I want to show that you can have non-trivial gauge fields emerging even if there are no rigid links. So for that, let's consider three particles in a plane. So I've drawn for you three particles with coordinates, three particles Z1, Z2, and Z3, each of them having coordinates x1, y1, x2, y2, etc. And they lie in a plane. And let's say that these are three particles and they interact via two body forces, like Coulomb force or gravitational force or something like that. Something that you're familiar with. Nothing very exotic. Okay. You can even take a simple harmonic xi minus zi minus zj the whole squared. You can even take a harmonic force, but we are only taking two body forces. Okay. And what we want to do is we want to study the deformations of this three body system. So what do I mean by deformations? The kind of motions of this system that I want to study is the following. Again, because there is no net external force and no net external torque, the center of mass does not move and the center of rotation also does not move. So because the center of mass does not move, I can choose my coordinates system to sit right on top of the center of mass. And after that, I can just ignore the center of mass motion, knowing that it won't move. Okay. So we're going to ignore the center of mass motion. And then let's look at the possible configurations just to understand what's going on. Notice that in figure A and figure B, all that has happened is that this object, this composite object, has merely rotated as a whole. I want to emphasize that now there are no rods, no rigid links between the particles. Okay, particles are free to move any way they like. I've drawn these lines between the particles only to sort of give a mentally to give an orientation, mentally to fix the ideas. But they are not rigid rods that connect these particles. Okay, so between A and B, there is just a overall rotation, and we are not going to worry about overall rotations because overall rotations of the type that take you from A to B come about by applying an external torque to the system as a whole, which we don't have. So we are going to declare that A and B are considered to be the same configuration. On the other hand, A and C are distinct configurations because the relative distances between the particles has changed. Similarly, C and D are the same configurations because you can do a rotation. You can rotate. If you don't want to rotate the bodies, then you can just rotate your coordinate axis. And you can, if you rotate your coordinate axis, you can see that the picture C goes to picture D. So here in the examples, A and B are the same, C and D are the same, but A and C are not. Okay. So this is nothing but three particles, three particles in a plane. You can think of it as three interacting atoms in a plane. Now the shape space, the configuration space is again obtained by factoring out all global rotations. And this one, for the example that I showed you, for this, the configuration space turns out to be quite exotic. So the configuration space turns out to be what is called a three-dimensional sphere quotiented by U1 times R plus, the positive axis. So I'm not going to go into it. It takes a little bit of work to arrive at this configuration space. It's not very difficult, but it takes a little bit of work. So I'm not going to derive it. And this is the configuration space, S3 mod U1 cross R plus. And for those of you who have seen, who know about monopoles, the dynamics of this 3-particle system in a plane is identical to the motion of an electric charge moving in the field produced by a magnetic monopole. Again, if this statement doesn't make any sense to you, don't worry. I just wanted to give this example as an example of a very simple system to start off with, but a system whose dynamics turns out to be quite exotic because its configuration space is quite sophisticated. Okay. More generally, suppose you have n atoms in R3. This is the kind of thing that that happens, that we study all the time. If you're studying molecules, or if you're studying a gas, that is our starting point, right? We are looking at n atoms. They move in R3. The shape space in this case too is obtained by factoring out the overall 3-dimensional rotations, and 3-dimensional rotations are SO3. In this case, the shape space can be quite complicated, both in terms of its geometry and topology, and even something as simple as 4 atoms moving in 3 space dimensions has a very complicated shape space. I will have occasion to refer to this problem later, refer to this particular shape space later, because amazingly enough, this shape space appears in the discussion of a SV2 non-abelian gauge theory. But that's for later. The shape space of 4 atoms in 3 dimensions is complicated. It is not a smooth space. It has edges and corners. And if you want to study this space, then we have to understand what it means to deal with spaces that have edges and corners that are not necessarily smooth. And we have no option but to study it, because as we said, the system is a very simple system, and sometimes we need to know the dynamics of the system. Now, of course, if we take the point of view that these are atoms, if we do take that position seriously, and there's no reason not to take it seriously, then it's not enough to study classical dynamics. We need to include quantum mechanics as well. And this is where the situation becomes really interesting. That is, when you do quantum dynamics of shape spaces. It's not as exotic as one might think. You are all familiar with the Born-Oppenheimer approximation, right? The Born-Oppenheimer approximation treats the atomic nuclei as stationary, and then once you choose them to be stationary, you solve for the electronic wave functions. Once you solve for the electronic wave functions, you go back and look at the locations of the atomic nuclei, and then you look at then you ask, if these atoms were not frozen but moved slowly, in other words, if the dynamics of nuclei is slow, then how does its quantum motion look like? And we do this all the time in chemistry or in molecular physics. We see that the spectrum of the molecule, if it's a molecule that we are studying, gets organized into rotational, vibrational, and electronic levels. If it's purely internal motion, then you can see that purely internal motion is nothing but combination of vibrations. What happens is that pure internal motion can affect rotational motion, and we saw this already. We had these rods. We moved the rods with respect to each other. So if you like, they were examples of vibrations. They were pure vibrations. They were pure internal motions. So in other words, they were like vibrations. But when we performed a sequence of internal motions, we found that the mechanical body as a whole rotated. Similarly, in molecular physics, internal motion can affect rotation. And this coupling between this is the source, if you like, of the coupling between vibrational modes and rotational modes. This is one of the most important consequences, the coupling between rotational and vibrational modes, and that happens almost without exception, in almost all molecules. The study of the spectra are called, I believe they are called row vibrational spectra, and is a very important part of spectroscopy. So whenever you see a coupling between rotational and vibrational spectra, it is a very clear observational signal that we have emergent gauge fields of the kinds that we talked about. Another effect, which I don't have too much time to discuss, is the Yarn-Teller effect. Again, it is the result of a very subtle interaction between the symmetry of the molecule and the emergence of a non-abelian gauge field. Okay. So let me just see. I've already finished more than 1 hour, so I should speed up a little bit. But let me make make a few more remarks about the things that we talked about, and then we'll spend some time discussing questions. So in all the examples that we looked about, the naive configuration space is too large to start with. For example, when we had 2 rods, the naive configuration space we thought is the space of 2 angular variables, but actually it's not. It's just 1 angular variable, and so on, right? The true configuration space is obtained by eliminating all the redundant variables, so getting rid of redundancies. What is interesting is that although the examples I showed you were from mechanics and a few others which had potentially molecular physics applications, these situations occur also in particle physics. And the simplest example is in quantum electrodynamics. And the way you see it is as follows. The wave function of the electron can be multiplied by a space-dependent phase. On the other hand, observables in QED are objects like currents and charge densities. And these are independent of the phase. They just depend on the modulus squared of the wave function. So QED has built into it a natural symmetry, which is the symmetry of this multiplication by a space-dependent phase. And this symmetry is nothing but the gauge symmetry with U1 as the gauge group. We say U1 because U1 is a mathematical way of describing a phase, and because you can make a phase change locally, a different phase, you can choose a different phase at different space-time point. This is a local U1 gauge symmetry, and the theory of charged particles which have a local U1 gauge symmetry is the theory of electrons and protons and electrons, or electrons and positrons, and photons. So this is the theory of this QED is a theory of U1 gauge symmetry. Okay. So next I will talk a little bit about non-abelian gauge theories, but this may be a good point to pause and see if there are any questions. There is a question from Shankaran Sahu who asks, do magnetic electrons moving in magnetic monopoles have gauge symmetry even at the quantum level, or is there an anomaly associated with it? I'm not sure if I understand the question, because electrons of our physical world have only electric charge. But
so actually, I have it should be only electrons. That's a typo.
You meant electrons. Okay. Now, electrons moving in the field of a magnetic monopole. If it's a classical electron, then the motion is given to you by nothing but the Lorentz force law, F equal to Q V cross B, right? Because you know B, the magnetic field produced by the monopole, you can solve for the motion of the electron. And this is what it is. Now, your question, of course, is what happens at the quantum level. At the quantum level, what you need to do is solve the Schrodinger equation. In other words, find the wave function of an electron that is moving in the background of a magnetic monopole. In other words, solve the Schrodinger equation for a particle moving in the background of a magnetic monopole. This has been done, and this is a well-studied problem, and it has been solved. I think the first person to have solved it may have even been Meghnad Saha. The first person to have studied it carefully may have been Meghnad Saha, but I'm not sure about that. But the answer to your question is yes, you can study this problem at a classical level, at the quantum level as well. And I'm not sure what you mean by an anomaly, but
So
there
I
is.
meant that, for example, we carry out the path integral, that is, and define e to the power I z of I z,
Yes,
and then write it as a functional,
yes,
and then suppose we can easily derive the Noether's theorem, right, with the help in case of with time ordered products.
yes.
So if we do that, then will this gauge symmetry be valid also there, or will there
Yes,
be any anomaly associated with this at this
there is no problem with there is no problem with writing down the path integral for a electron moving in the background of a magnetic. Is there any other question?
Yes, sir. I had a short
Yeah.
question. You've
Yes.
been saying that the existence of you're saying that these gauge symmetries are emergent from the existence of a constraint in the system, right? A non-holonomic
That's
constraint.
right. Yeah, a
Is this in
non-holonomic.
any way, this seems to be closely related to the Noether's theorem, because there we have the flip side, because the existence of a symmetry there implies a conserved current, which then acts as the conserved current can be used to constrain our phase space, right? So
Yeah.
if you could clarify whether there is
Okay.
a relationship between the two.
In the situation that we are studying, what we have is a non-holonomic constraint, and the non-holonomic constraint leads to the emergence of a gauge field. As such, so to speak, we have no symmetry in the theory. The symmetry is it is misleading to think about this as a symmetry, because the transformation that we do is a transformation that is done to eliminate redundancy. The symmetries that are usually discussed in the context of Noether symmetry are transformations, group transformations, or other symmetry transformations, where where the original configuration and the symmetry transformed configurations are both distinct, physically distinct configurations. These physically distinct configurations, when you have a transformation by a group or something like a group, it might be an algebra, but let's just stick to groups. But so when you have a symmetry transformation where the initial configuration and the final configuration are physically distinct, then if this transformation is can be done continuously, then Noether tells us that underlying this symmetry is a conservation law. For us, the transformations that we are doing lead to the same physical configuration. The original shape of the mechanical arm is the same as the final shape of the mechanical arm when we do gauge transformations. So in that sense, gauge transformations are not symmetries in the sense of Noether. Nevertheless, gauge transformations are transformations that are often based in groups. So it might occasionally confuse us into thinking that, oh, we are making a transformation by a group, so therefore it should be a symmetry. But the correct way to think about this transformation is whether the transformation by the group leads to two physically distinct configurations, or whether it gives you the same physical configuration. If it gives you the same physical configuration, then we are talking about redundancies, and there are no symmetries a la Noether associated to these transformations. I hope I have answered that question.
Yes, sir. Thanks for the clarification.
Is there any other question? Okay. So I have yesterday, I think I finished too quickly, and today I will, I might take more time than than I'm allotted. So let me apologize in advance, and also let me try to speed up a little bit. Okay. So as I said, the possibility of gauge symmetry is there in particle physics as well, and the simplest example is that of QED, where the gauge symmetry is that of a U1, where the gauge group is U1, the group of phase transformations. It turns out that you can have more complicated groups as well. And quantized shape spaces also occur in the study of QCD, or quantum chromodynamics. So depending on which part of your BSc or your MSc course you are, some of you might have heard of quantum chromodynamics. It is a theory that tells us that quarks come together to form protons and neutrons and pions and various other particles that interact via strong interactions. QCD is a theory, it's a dynamical theory. In other words, it gives you the dynamics of how these quarks come together to form protons or neutrons, or it is supposed to do that anyway. It's a dynamical theory where the underlying gauge symmetry is now a non-abelian, based on a non-abelian group. I think you are now familiar, because of Professor Dasgupta's classes, what a non-abelian group is. A non-abelian group is one in which the order in which you take the product of two group elements matters. So A times B is not the same as B times A. And S3, the permutation group permutation group on three objects, is the simplest example of a non-abelian group, because if you write out the multiplication table, you will see immediately that the product of two elements is not the same if you exchange the order of the elements. The non-abelian group that we are looking at is a generalization of the finite groups that you looked at in Professor Dasgupta's class. These are examples of this is a group, for example, for QCD, it's a group called SU3. Now, I don't want to throw you off too much by non-abelian groups. You're already familiar with one non-abelian group. It is a group of rotations which you have studied, which you studied carefully for the first time already in your BSc, right? You know that if you take two generic rotations, then the product of two generic rotations is not the same if you do the rotations in the opposite order. So if you do a rotation, follow it by another rotation, and you did it the other way around, the final configuration of the body will be different from in each case. So SU3 is just a slightly more complicated version of SO3, the group of rotations. Now, QCD was first proposed about 60 or 70 years ago, and it has been heavily investigated since that time. But many of its aspects, very important ones, are still a mystery. And the picture that I have for you, the sort of cartoon picture I have for you, is the picture of the phases of QCD. As you know, you might have seen a picture like this for a phase diagram of water, where you have a line of first order transitions that terminates at a second order point, and that is the triple point of water. You can see that the phase diagram of QCD is much more complicated, and in that it has all these different domains, each of them corresponding to a different phase of nuclear or quark matter. So this is the reason why, I mean, this diagram that we know that I have shown you here, even today is the understanding is fairly impressionistic and not at all, not as precise, definitely not as precise as we know the diagram for the phase diagram of H2O. Okay. Now, it is this gauge symmetry, the kind of thing that we talked about earlier,
Professor?
that makes QCD both interesting and challenging and frustrating. Yes.
In that
Yes.
graph,
Is there a question?
yes, in that graph, to the y-axis, it is presented by t and x-axis mu. What do they mean?
Yes.
T and mu.
Yeah. So the y-axis is the temperature, and the x-axis is the chemical potential of quarks. So as you increase the chemical potential, but do not change the temperature, even if you are at very low temperature or formally at zero temperature, but you keep increasing the chemical potential, which means you, roughly speaking, you keep increasing the average number of quarks. You see that you change from the vacuum to nuclear matter to non-CFL quark fluid to CFL quark CFL quark condensate. If you change the temperature, if you start increasing the temperature, then at some point you reach this phase quark gluon plasma, which you might have heard of at this, or maybe even heard some popular talks about them. So I don't want to discuss too much about this diagram. We can discuss it after the talk. I put up this diagram here just to show, just to emphasize that the phase diagram of QCD A is not fully understood, because you know, mentally you can recall the picture for the phase diagram of water, and that is a much simpler phase diagram. And that was the reason why I put it up, is to emphasize that many important aspects of QCD still remain a great mystery to us. Okay. Does that answer your question?
Yes, that clears a lot. Thank you, Professor.
Okay, sure. Okay, so let's go on. One of the most important questions is, what are the physical states of QCD? So this is a more formal way of asking the question, what are the phases of QCD? So at any given temperature, pressure, and chemical potential, what is the ground state of the theory? What are the properties of the ground state of the theory? So the question about physical states is really this question. And this has implications for a variety of things. It has implications for the masses of elementary particles, the quark gluon plasma, exotic quark matter, nuclear matter, you know, many of the super dense stars, neutron stars, being just one example. What is the state of nuclear matter in that inside a neutron star? Do we understand it? And it's very important to understand these, because nowadays LIGO, for example, is able to investigate collisions and mergers of neutron stars by looking at the gravitational wave production. So it is now becoming more and more important for us to get control on understanding what is inside a neutron star, if we want to fully exploit the data that comes out of detectors like LIGO. The first point, which is the masses of elementary particles, what I mean by that is that you can write down the Lagrangian for QCD, but starting from there, to predict the mass of the proton, the neutron, the pion, the kaon, whatever you like, is a long and almost impossible step. It's very long. One of the reasons for that is that QCD is a non-abelian gauge theory, and the non-abelian nature of the gauge group makes it, in some ways, very, very fundamentally different from the other gauge theory that we know of, which is QED. So because of this, because of the non-abelian nature, we are able to make confident predictions confident predictions that we are able to make, especially at low energy, are very few. Okay. So at very high energies, we have a reasonable understanding, and equivalently at very low densities, because perturbative calculations, perturbative quantum field theory can be used quite reliably in these regions. But in any region that is away from here, if you have high density, or if your energies are low, or if your temperatures are low, our understanding is quite poor. Okay. So let me give you, this is a perhaps the shortest introduction to QCD that you will see anywhere, and this is just to tell you, give you an idea of what are the ingredients, what are the rules of the game if you want to play the game of QCD. So the rules of the game are based on a gauge field, A mu, that depends on space, that depends on space x as well as time. There is a gauge symmetry. That means at each point of space, and each space-time point, you can transform the gauge field by a SU3 transformation. Okay? It turns out that this transformation is a redundancy. So we must factor it out, just like how we did for the case of the two-hinged object or the three-hinged object. Remember, we factored out, we got rid of the redundancy. So the true configuration space is nothing but the space of all gauge fields factored by the space of all gauge transformations. And it turns out that this is a furiously complicated object. It has very, very sophisticated geometry as well as topology. Even the simple example that I gave you of 4 particles in R3, right? That was such a simple example. You can easily imagine this. You can even imagine such a situation of 4 particles in 3 dimensions. But the configuration space of 4 particles in 3 dimensions is again very complicated. So you can imagine how intricate the QCD configuration space is. And just like that one, it has singularities. So singularity is, roughly speaking, are places where the space is no longer smooth. And intuitively, you can think of it as potholes. Space is not smooth, so it's like potholes. And in fact, it's more than potholes. Sometimes there are holes through which, if you fall, you will emerge in a completely different part of space, of this configuration space. And if I have time, I'll briefly tell you what happens when you fall through a rabbit hole. This rabbit hole is a reference to Alice in Wonderland. If you remember, Alice as a little child fell through a rabbit hole and emerged into a mysterious and wonderful space in which she had many adventures. So that's the kind of thing that happens in QCD2. If you go down the rabbit hole, you emerge into a region that is often an exotic phase of QCD. Okay. Now, because the theory is so complicated, you can make approximations if you want to make progress. For instance, a lot of QCD studies are done by turning off the quarks. So you have no quarks, you have only the gauge field. Even in this situation, you can you can make a further approximation, which is that I'm going to look at gauge fields that are independent of space. That is, that they depend only on time. So now it turns out that the space of gauge fields turns out that it is finite dimensional. It's nothing but the space of 3x8 matrices quotiented by a particular action of SO3. Don't worry if it doesn't make too much sense to you. All I'm saying is that in this approximation, the configuration space, instead of being infinite dimensional, is a finite dimensional space. And remarkably, it still retains some memory of its geometry as well as its non-trivial topology. And in this approximation, for example, you can compute the masses particles. So if you have no quarks, if you have only QCD, only gauge fields, then the particles are called glue balls. And I've shown you here computation of glue ball masses from the approximation that I made, and I've compared it with the computation that lattice people make, in which they don't make any such approximation. And you can see that already with the approximation that we made, in which the space in which the gauge fields do not depend on space at all, you do pretty well. You do very well, quite well. Well, in my opinion, very well in terms of predicting the masses of glue balls. But of course, if you want to do QCD, if you want to study the theory of our universe, then you have to add quarks. So again, you can add quarks and study the theory in this approximation, and you can compute the masses of these particles. And here I've shown you the predictions from the matrix model, which is a model of QCD where the gauge fields do not depend on positions, versus the experimental values. So here, for example, if you look at the proton, the nucleon, which is n/p on the horizontal axis, you can see that the prediction of the matrix model is almost bang on top of the value from nature. Similarly, for the particle next to it, the cascade, the capital sigma, the sigma star, the cascade star, omega minus, all these particles, many of them, most of them come within the error, the real value, the value from nature is within the error bars that come from the matrix model prediction. There are a few particles, the K star and eta, where there's the K eta and the eta prime, where the matrix model prediction is way off from the actual value. But apart from these three particles, the predictions of such a crude approximation give you very good answers for masses of QCD. Okay, so I just want to briefly tell you about these wonderful rabbit holes that you can go through and come out. And when you come out on the other side, you will be in a different phase of QCD. So these are phases that exist even at zero temperature, because these are phases that can exist that correspond to finite values, to finite quark condensate densities. So it's like you have quarks and they have condensed to form a quark condensate, and this corresponds to a new phase. And you can see exotic phenomena like spin color or color flavor locking in some of these phases. So I have drawn for you here the configuration space for SU2 gauge theory. This is not the same as the non-abelian gauge theory for strong interactions of our universe. It's a slightly simpler theory, but still sufficiently complicated. And with a little bit of work, you can show that the bulk, which is light blue in color, corresponds to one phase of the theory. And there is one rabbit hole at the tip A. If you go down that rabbit hole, you emerge in a world, or emerge in a different phase of the theory. And similarly, there's another distinct quantum phase of the theory at the tip B. So this theory, depending on the quark content, has either 3 or 4 distinct phases. Okay. So I want to end here. I think I've taken 10 minutes more than I should. Just want to summarize that even for simple classical systems, the non-holonomic constraints can lead to very interesting geometric and topological properties that lead to fairly complicated and non-intuitive dynamics. Emergent gauge fields have a Coriolis-like effect, and therefore can impact the dynamics quite significantly. This is, of course, in classical systems. When you go to quantum theory, this quantum dynamics of shape spaces can lead to an alternative and very often a deeper understanding of molecular systems. And the last thing that we discussed was in high energy physics, where shape spaces, exactly the kind of spaces that we discussed earlier for those mechanical systems, shape spaces, but exactly the same kinds of spaces, they describe QCD. And the study of the dynamics on these shape spaces can give us interesting new information about the phase structure and the spectrum of this theory. Thank you very much. And here are the references from which some of the material that I showed you was taken. Okay. We can take a few questions now. I will leave it to Atri to decide whether we have time or not. Hello?
We can take a few questions.
Okay, I'm here.
Hello, Sachin.
Yeah, I'm here.
Yeah, so we can take a few questions. Though we are like over time, we have crossed the time limit, but still we can take at least 5 minutes more.
Okay,
And since you don't have another lecture tomorrow, so it's nice to answer the queries.
Fine.
I mean, the students will feel better, I think.
I am here. So fire away.
Professor?
Yes, yeah.
I cannot map the two facts, whether you discuss the U1 symmetry in QED. Actually, we find the gauge theory to conserve the local U1 symmetry, right? When the phase transformation is space dependent, then for the symmetry, I have to come with a gauge field. But now in this topic, you are saying that a gauge field is built up in QED because of some kind of non-holonomic constraint. Is it something analogical? I can't map this.
Yes, that's exactly right. So let me say this a little bit slowly. We argued that if you take a wave function of an electron, then you can multiply it by a space-dependent phase, which is a U1 phase. And then if you sit down and carefully write down the Lagrangian by demanding covariance, then you realize that you have to introduce a gauge field corresponding to this U1 phase, and the dynamics of this gauge field, that the dynamics that you demand for this gauge field is nothing but the dynamics of the photon, right? So the origin of the photons is in the gauge field. So in QED, we have, if you like, there are two types of objects. One is light and one is matter. Matter and light talk to each other as long as matter is charged. Yes. Now, in the case of QCD, although I didn't have time to say it, you can make the same argument. Instead of electrons, the object that you have in mind is a quark. It turns out that the kind of quark we are interested in is a 3-component object. And the transformations that you can, let me say that a little bit better. The wave function of the quark is a 3-component object. And the transformations that you can make on this 3-component object is, instead of a single phase, you multiply this 3-component wave function by a 3x3 unitary matrix of determinant 1. In other words, by a SU3 matrix. So this is the analog of a phase. Hello?
Sorry, I can't hear you. Yes.
I think that there was I think there was a momentary network disconnection, but can you see my slides and can you hear me?
Yes, I hear you.
Okay. Okay.
Hello.
Hello.
Yeah, I can't hear any of you. Hello.
I can hear you, ma'am. Maybe Professor. Yes, yes.
I think Sachin's network is not working.
Okay. Can you hear me now?
Yeah, it's
okay. Yeah, I'm not sure what is happening, but so let me try to answer your question quickly before the next network disruption. So the analog of the photon is the gluon, and then there is a Lagrangian to describe the dynamics of just the gluons. So the gauge field in the case of QCD is the same as the gauge field. It has the same status as the gauge field in the case of photons. The details are different, and the difference in details is important because the two theories have very different behavior. Okay. Is there any other question?
Hello, sir. Hello, sir.
Yes. Yeah.
I am Harkishan. I had asked you the question
yes.
regarding how we can calculate the deduce and find the Raman modes and IR modes of a periodic structure for a given point. So, if you could say something about that.
So the basic thing that you have to do is to look at the molecular vibrations. For example, if you are looking at Raman modes, and to organize the molecular vibrations according to the various representations of the point group symmetry that you have. I think that part of this exercise was done yesterday for a very simple molecule, for a molecule in the shape of a square in your group theory class. What you need to do is, the basic idea is the same. You have to look at the characters, and you have to organize the various modes, normal modes, according to characters of the underlying characters of the representations of the underlying point group. I can't say more than this without paper and pencil. Yes, but I hope that it is at least partially answering your question.
Okay, sir.
I'm not sure. I'm not sure if I understood your question. What you had in mind, but okay. Maybe if there is another question.
Harkishan can write it to Harkishan. You can just write it up what you are feeling and mail it to sir so that he can read and try to explain you. It may be one-to-one discussion, right?
Yes. Okay, ma'am.
Okay. Is there any other question, or should we stop now, Atri?
Anyone?
Hello? Hello? Hello?
I think now it is Atri who's got disconnected, I think.
Okay. But can you hear me now?
I can hear you.
Yeah, we can just possibly we can stop.
Yeah.
Okay. So thank you very much.